So this is problem number 2. It's from the 2015 AB exam. And this is a calculator question. And they give us two functions, f and g. So f is defined right here. So it's got this exponential piece to it. And then g is defined right here. So g is a polynomial. It says R and S are going to be the two regions between F and G as shown in the first quadrant right here in the graph they provided us with. And what we are asked to do in part A is we're asked to find what the sum of the areas of regions R and S actually turns out to be. So if we handle this in two pieces, the first piece would allow us to find the area of R. You take a vertical slice of region R, the top of any vertical slice you draw is on the polynomial function, and the bottom of any vertical slice you draw is on the exponential function. So you approximate that vertical slice to be a rectangle, and the height is going to be the top y value, which is on the polynomial, minus the bottom y value, which is on the piece that involves the function that involves the exponential piece. And then the width of that, the width of this slice is some tiny, tiny difference in x's, so that's delta x. The area of this one slice is going to be approximated by taking the height times the width. We want to add together the areas of a bunch of these slices, and we're going to let the definite integral do that work for us. So we're going to integrate this approximation. The limits of integration have to be the x values that all slices with this set of dimensions range between. Well, the smallest x value that this type of slice is going to take on is going to be the x of 0, and the largest x value is going to be the x at this intersection point. Now, this is a calculator question, so you can go ahead and you could graph these functions on your calculator and figure out that the x-coordinate at that intersection point is right here. Now, what you do not want to do is round that to 1.032 or 1.038, or excuse me, 1.033. You're going to want to take all of the accuracy that you can from the calculator's intersection point there, only because if we round this off and do more math with a rounded off number, we're going to lose accuracy in our final answer. So I'm just taking all of the digits of accuracy that I had access to from the calculator there. Similarly, when we go to the region S, we take a vertical slice of S. The top of any slice is now on the exponential piece minus the y value at the bottom, and the bottom is the y value on the polynomial. So the height of that slice is approximated by taking f of x minus g of x, and then the width is still delta x. So here's the area of one of those slices. We're going to add together the areas of many by using a definite integral, and the slices that have those dimensions are going to range between the x values of 1.03 and 2, the x value at this intersection. So since the calculator's in play here, we can evaluate this integral on the calculator, we can evaluate this integral on the calculator, we can sum those results, and we're going to get the area total between these curves for the region R and the region S. So the input for that is a mess. You notice I have another option for the way you can do this on the calculator. If you notice that with these two different types of slices, we want the height of one of these slices to be positive. So for region R, we did big Y minus smaller y. For region S, we did the big Y, which now happens to be on F, minus the smaller y, which now happens to be on the graph of G. These formulas are basically equivalent if we take the absolute value of them. So what I noticed was I could just do the absolute value of f of x minus g of x and do one integral clear from 0 to 2 rather than having this big mess of an input and running the risk of getting one parenthesis in the wrong spot and missing the result because of it. So a couple different ways you can formulate your final answer there by utilizing the calculator. They both get you the same result. You do notice that we have a slightly different answer here than we have here, and the reason for that would be because you'd notice something that's been rounded off right here. So I've lost some accuracy out in the digit after the 4, but that doesn't matter for the purposes of the AP exam because you have to be accurate to the third digit beyond the decimal. But if I would have rounded this off to 1.033, I maybe would have gotten a slightly different answer than what I should have gotten for the one that involved the approximation. When we move on to Part B tells us that region S, so we're done with the region R, at least for the purpose of Part B. Region S is the base of a solid, so something is sitting on region S here. This is the flat base of it, And if we take a cross-section of that solid perpendicularly to the x-axis and remove it from the solid, what we're going to be looking at is we're going to be looking at a square face. So here was my attempt at drawing a square face. This flat edge on the right side of the cross-section that I've drawn, if I was to replace that between the two pieces of the solid that sit here and here, this flat edge is going to have to sit perfectly back down into the flat base of the solid. That allows you to figure out what the dimensions of this square cross-section are. So we have a height of bigger y, which is on the exponential, the piece of the function that involves the exponential piece, minus the smaller y, which is on the polynomial. So that's going to be f of x minus g of x for the height of this cross section. Well, it's a square face, so that's also going to be the dimension across the bottom. And then the thickness is the width of the slice in the coordinate plane, and that's a tiny, tiny difference in x values. So the volume of this one cross section can be approximated by doing base times height times width, or since it's a square face, just this squared times delta x. I want to add together a bunch of those cross sections volumes, so I'm going to use the definite integral as a tool to do that. And if you do that on the calculator, what you end up with is 1.283 rounded to 3 digits of accuracy, and I did it in part A. I should do it here too. Wouldn't impact your result on the AP exam whether or not you got credit for this, but I used generically square units for my area for part A, so I used generically cubic units for my volume in part B. The last piece of this is a little bit different. It's not that difficult. You just have to kind of realize what it's going for here. So it says h is going to be the vertical distance between the graphs of f and g in the region S. So what is your formula for h? Well, your formula for h is going to be at 1.8, the bigger y, which is on the function that involves the exponential piece, minus the smaller y. So here is h at 1.8. We can find what h equals by doing f of x minus g of x, the function that involves the exponential piece minus the function that's the polynomial. The rate that height is changing is going to be given by the derivative of h with respect to x. We need to evaluate that derivative at 1.8. Now, the long way to go about this would be to put f of x here, put g of x here, do the derivative of that manually, and then evaluate that derivative at 1.8. Since we don't necessarily need dh dx in a general form, we just need to know the value of it at the specific x of 1.8. What you can actually do is you can use the numerical derivative option on your calculator, and you can type in what you want the derivative of. So here's f of x minus g of x in a set of parentheses. Watch out for that set of grouping symbols around g. I'm doing this derivative with respect to x. I'm evaluating this derivative at 1.8, and there is the rate that the height between those functions is changing at the x value of 1.8.